Okay, yeah. So is the mic catching me? Are we okay? Okay, fantastic.
How do you pronounce it?
So in Dutch, Okke Schrijvers, but anything that sounds anywhere close is fine. I don't judge. Yeah, so today I'll be talking about some work I've been doing with my advisor at Tim at Stanford that we'll be submitting soon. So I guess you'll guys be a test audience to see if it'll do well in the community. And it's about online prediction with selfish experts. So I want to start with the motivation for the problem. And the motivation for the work comes from 538. So just a quick poll. Who here in the audience has heard of 538? Pretty much everyone. Okay. Leading up to the election, who checked it about every hour? Wow. Okay, I was not alone. Yeah, so 538 is a company that consists of a bunch of statisticians, and they write about different things like sports and politics, and they take a sort of a statistical approach to it. And for the purposes of this talk, what's going to be important is that they also make predictions about US presidential elections. And they do that pretty well. So in 2012, not only did they correctly predict that Obama would win the re-election, they actually managed to get every single one of the states correct, meaning that whichever candidate they had in a state with the highest probability ended up winning that state. So that's impressive considering the total state space there.
Do they get also those states where it's relational, like not all electors?
That's a good question. I should have looked that up. I'll get back to you on that one.
That's sort of not calibrated, getting every one of them.
Yeah. That's true. So they corrected for it in 2016. Yeah. So in 2016, I think all of the reliable sources were off by a lot. But out of the reliable sources, arguably 538 did fairly well. So they put on the day of the election, they gave Trump about a 30% chance of winning. And for those who have been asleep for the past 2 months, that's the event that ended up materializing. So they're doing pretty well. Which is kind of surprising, seeing as they don't do any polling of themselves. So how do they do this? I want to spend just a minute on sort of explaining how 538 works, at least to a first-order approximation. So they start by taking a bunch of polls taken by different pollsters, and each of these pollsters have some kind of opinion, some kind of prediction about what the chances for the different candidates are. And what they do is they assign a weight to different pollsters. And the way that they assign these weights is sort of based on the past performance of pollsters as well as a couple of other things. And then they take the different predictions and the different weights, and they take a weighted average. Now, there's a couple more bells and whistles that are at play here, but this is sort of a first-order approximation of what they do, and for the purpose of this talk, this is going to be the relevant part. So I want to talk about these weights for a little bit, though, because these weights are obviously important for 538, because their prediction sort of crucially depends on it. But they're important for the pollsters themselves as well. Why? 538 makes these weights public. So you can go to the website, you can look at the address on the bottom here, and you can actually see how every pollster is weighted in the 538 prediction. And this weight sort of carries in it the idea of how highly valued 538 thinks that this information is. So if you look, for instance, at the top entry, Survey USA, it gets a 538 grade of an A, which in the American grading scheme is about the highest that you can get. So they're a very reputable source. Whereas if you look near the bottom, Research 2000, they get an F, which is not a passing grade. And as a matter of fact, this pollster has been banned from the 538 prediction, so they're not using that at all. Now, why is this important? So first of all, just in terms of reputation, as a pollster, you'd like to get a high grade, obviously. But also think of it in terms of future revenue. This information is public, and if you want to have some polling done, who are you going to get? Are you going to get the research agency that is not even considered anymore by 538? Probably not. You're probably going to more likely choose pollsters that are ranked a little bit higher. And so this sort of has revenue impacts for these pollsters in the future. So that's kind of the problem that I want to look at. So at a high level, do the existence of these weights that these pollsters care about, do they in any way impact the reports that these pollsters make? And if they do, in what way? Now, obviously, it seems that the incentives are aligned here, right? Because the weight is supposed to capture how reputable a source is or how good the information is. And so at first glance, it seems like pollsters are just incentivized to have sort of good information. But we all know that in order to actually make that claim confidently, we first need to write down the math and see if it actually works out well. And just sort of taking a step back, as a general problem, I think of this as incentives in machine learning. And we also heard from Moshe earlier today about how, so machine learning is taking off, it's exploding in popularity, and you see it everywhere from self-driving cars to how we browse on the internet. But the existence of these algorithms may very well create incentives. So Moshe talked about information retrieval and how sort of the existence of a search algorithm may impact what kind of content people create. And this is sort of a different instance of the same problem. So that's the problem at a high level.
What are the weights based upon?
So that's an excellent question. And in order to answer that, we need to look at a very specific model. And so let me describe a specific model that I think is more or less the first model that most of us would come up with. It's certainly not the only one. But I'm going to talk about expert prediction with, online prediction with expert advice for a little bit. And so we also heard from Theodoros in his last talk about this. And there's a bunch of different variants. So as a quick cheat sheet, I'm going to say that we're considering the full information setting, not the bandit setting. I'm going to go into detail first, but this is the cheat sheet. Full information instead of bandit setting. We're going to look at binary outcomes instead of large outcome spaces, and we take adversarial realizations instead of stochastic ones. I see a question over there.
So, but can you tell us in a specific example how the weights are determined, or actually?
For 538, I can talk about that for a long time, but I'll take that offline. We can chat about that offline. But part of it is past performance, but there's a number of factors that go into it. I'll be focusing on a model in which past performance very directly leads to how the weights are determined. So I'm assuming most of you will have seen this model before, but I do want to spend just a little bit of time talking about it. So over a number of time steps, the following things happen at each time step. First, there are n experts that make some kind of prediction. In this case, we have binary outcomes, so their prediction is captured by a single number between 0 and 1, where 1 corresponds strong advocacy for the event 1 materializing, and 0 corresponds to strong advocacy for that event not materializing. An online algorithm gets to observe these predictions, and then based on that, makes their own prediction. We're going to get into how they do that in just a second. Then an outcome is realized, and the algorithm incurs a loss based on whatever their prediction was and based on the realization that was observed. So the loss, we parameterize that specifically here because for different applications, sometimes different loss functions can make more sense. So it can make sense to have a quadratic loss function or an absolute loss function or different loss functions for different application areas. And in particular in machine learning, people kind of use the one that works well for the specific problem that they're working on. And an algorithm that works really well in this particular setting are different versions of the multiplicative weights algorithm. So in here, we calculate a weight for each of the experts. And after each time step, we update that weight by taking the weight of the last time step. Is this working? Oh, it is, but the battery's low. OK. So by taking the weight at the last time step and then multiplying that by some function of what the prediction of an expert was and what the realization was. And then the next step is that the prediction of the online algorithm is some weighted average of the predictions of the different experts. So these algorithms, and sort of it's for different choices of f, you get slightly different results, but in general, the kind of results that you can expect if you have a deterministic algorithm, you can get a loss factor of 2, meaning that the algorithm incurs a loss that's at most twice that of the best expert in hindsight. And in the randomized setting, this is no regret. And I'm being just a little bit informal with the guarantees here, because there's some extra factors that I'm omitting. And the no regret is a vanishing regret in the same sense as the Doris mentioned just before. So, sorry. So I talked about what so this is a model that sort of captures weights and makes predictions based on weighting of different experts. But this model doesn't instill agency in the experts. So in order to talk about how experts may behave, we need to look at a model in which they can make decisions. So we slightly changed the model and replaced the first step with the following two things that happen. First, each expert formulates some belief about the event that is about to happen, and then they report a prediction. And the question is, will experts report the prediction that corresponds to their internal beliefs, or will they somehow report something else? Now, in order to talk about what the expert will do, we have to say what the expert cares about. And so in this case, the utility of an expert is simply their weight at the next time step. So this sort of captures the idea that because future revenue opportunities for an expert are related to the weight that they're assigned, they want to make sure that they maximize their expected weight. So I'm going to go into what we will try to do in this model on the next slide, but so far is the model at least clear?
So the belief you're assuming that they're like really the best they can do from their information without any incentive constraint?
Yes, yes. Think of it as exogenous. So it's some exogenous belief that expert may have. The loss for the belief.
I think that for the probability 20% A data, 30% B, 40% C, and now you need to give me a loss function so that I need to return one answer.
So we have binary. Sorry, I don't get it. We have binary outcomes, so a prediction is captured by just a single number, but I don't think that's what you were getting at.
So if you give me 0, 1 loss, then if I think it's about 50%, I believe it's
So experts in this setting care about their weight only. So their loss, in a sense, is fully captured by the weight that they're assigned by the algorithm. They don't have an intrinsic loss function that they care about. Yes. A belief is a distribution over 0, 1, which is a single number. Okay. So with this model, what are questions that we're interested in asking? So I said that we parameterize by the loss function because in machine learning, different loss functions are more applicable in certain situations than others. So we want for different loss functions L to answer the following questions. One, what is the design space for truthful algorithms? Where truthful here refers to if an expert has a private belief B, will their prediction match their private belief no matter what their belief is? So what are the algorithms for which this is true? Secondly, within that class of algorithms, are there any algorithms that have good performance guarantees? And thirdly, is this strictly harder than the classical model, meaning that the sort of the presence of agency of the experts, does that negatively impact what we can do or what regret guarantees we can hope for? Amos?
It seems to be only a function of the loss function rather than of how the weights are updated. It could be that there's many different ways of updating the weights, and maybe it's a function of that function rather than the weight, the loss function itself.
So the loss function will typically impact the way that the weights are updated? Not uniquely determined, that's true. We will see that for certain loss functions, You know what? I don't want to give away the clue yet. So hopefully it will become clear in the next 2 slides or so. If not, please ask that question again.
So do you normalize that weight?
That is an excellent question. So the algorithm typically, in order to make the prediction, weights are normalized. That introduces a bunch of weird dependencies that we're trying to abstract away from. So for the purposes of the expert strategies, we're assuming the weights are not normalized. Yeah, I can get back to why we do that later, but it gets kind of messy. Yes?
What do you mean by the third question, harder than the classic? Because there in the classical model we assumed adversarial, the experts could be adversarial, so that may include also if they are conspiring to lie or whatever, and
Yes.
then the guarantee is hold. So how can this be?
Let me think what the right way to explain it that is. With respect to the expert reports, you're always going to do as well as the guarantees of the classical model. Absolutely. With respect to the expert beliefs, this may no longer be true. So the third question specifically refers to that.
So you
Yes.
insist on truthfulness, basically? You'd like to, so you
By
design
current, yeah.
scoring rules? You are designing scoring rules for several agents simultaneously, basically.
Yes. So currently, by fiat, I care only about truthful mechanisms. I will go to a result of non-truthful, a non-truthful approach. And yes, the scoring rules I'll get back to. Yeah.
So the scoring rules would be the answer to the third question. The classical model is just scoring rules.
Okay. I'm going to ask you to hold that question for a second because there's a lot of good ideas in the audience, and some of them I was going to set up later in the presentation. So I'll get back to that. So let's first look at a loss function that, at least in machine learning, is used a lot, which is that of quadratic loss. So this means that we have a weight update algorithm for multiplicative weights, where the weight at the next step is 1 minus eta, where eta is a learning parameter, times the quadratic loss, and then that all times the weight at the last time step. That's sort of the standard way of doing the weight update with a quadratic loss. And it's not very difficult to see by a simple calculation that this, if we use weighted majority with a quadratic loss function, that this is a truthful mechanism. So if we care about quadratic loss and we use that weight update function, then everything simply goes through. So if we look at our goals, we can kind of say that we achieve every single one of them without having to do anything. Granted, we don't have a great idea of the design space for truthful algorithms yet, but at least the first thing that we try is in that space. So at this moment, let's just forget about defining that space in its entirety. Now, if this were to be true in general, this would be a very, very short talk. So let's look at a loss function for which things are not quite as easy. So if we look at the absolute loss function, here we have sort of the same standard update rule, 1 minus eta times now the absolute loss times the last weight. And in this case, weighted majority with the absolute loss updates actually incentivizes experts to name the most likely outcome as opposed to their true belief. So if they think that there's a 51% chance of something happening, they'll report that event with 100%. And this is, for instance, what you often see with political pundits who tend to make rather certain claims, even when they're not warranted. But this is a problem, and this goes back to the question that was asked earlier, because with respect to the reports, we still have good guarantees. However, with respect to the agent's beliefs, we can show that in the worst case, this algorithm has a loss factor that's at least 4 times as bad as the best expert in hindsight, at least with respect to their private beliefs. So we actually do a factor 2 worse than in the classical setting if we ignore the incentive issue altogether. And so this motivates looking at truthful algorithms in order to hopefully do any better. So, yeah, thank you. So recall the goals that we have. Now it makes sense to sort of look at each of these individually and try and answer this for the absolute loss function. So what about truthfulness? And this was actually answered from the audience, or there was a remark from the audience about this. So if we look at the multiplicative weights update rule, the important thing is this function f here, because that's the only place where the prediction and the realization are important. And if the expert maximizes their weight at the next time step, if we simply expand this out with the expression, then what we can see is that really the only thing that the expert cares about is the expectation of that function. Now, I'm assuming at least half of the audience will be familiar with strictly proper scoring rules or proper scoring rules. This unsurprising proposition shows that in order to have a truthful algorithm, we need to make sure that the weight update rule is a strictly proper scoring rule. So for the algorithm to be truthful, we're sort of restricted to weight update functions that are scoring rules. And with this in mind, it's also obvious why the quadratic rule works so easy, because that is a strictly proper scoring rule. And it's also obvious why the absolute loss function did not work out of the box, because it's not. So this sort of characterizes the design space for truthful algorithms. We need to use strictly proper scoring functions in order to update the weights. But if we're limited to just using strictly proper scoring rules, can we still get non-trivial regret guarantees if we care about absolute loss? That's not obvious at this point. Consider the spherical proper scoring rule, and don't try to interpret it, but I do want to point out 2 things. One thing is that we still have this learning parameter eta there, so we can use this in the setting where the learning parameter varies. Also observe that the absolute loss appears in the numerator on the right, meaning that we can relate it to the absolute loss of the algorithm eventually. And in the bottom, we have some kind of function that we can bound. With that, if you do the math, we can show that if you have a multiplicative weights algorithm in this setting, then in the deterministic case, so I guess the weighted majority algorithm, then the loss of the algorithm is at most 2 plus square root 2 times that of the best expert in hindsight. And there are some extra factors here like the log n and the eta. Eventually you balance the eta, and as t goes to infinity, you get the sort of the asymptotic result that there's an upper bound factor of 2 plus square root 2. And note that this is better than the factor 4 lower bound that we had if we ignore the incentive issues. So even though this result is not as good as we had with altruistic experts, at least it's better than the result that we had if we have selfish experts but we ignore the incentive issue. So, but it's not as good as with altruistic experts. So the question is this strictly harder than the classical model, at least for the absolute loss function? And so, unfortunately, the question here is yes, it is strictly harder to do. And the way that you prove that is sort of at an intuitive level. In order to prevent extreme reports from experts, we somehow need to reward them for uncertainty that they report. This introduces the notion of a scoring rule gap gamma, which sort of depends on the specific geometry of the scoring function, and not just the scoring function itself, but a normalized version of the scoring function. Remember that we have a learning parameter eta that goes to 0. So if we just try to prove it for a fixed scoring function, it's really easy to prove that there's a strictly larger than 2 lower bound. But we need to make eta go to 0 and for it to still hold. So with that scoring rule gap, we can show that in the worst case multiplicative way, a weighted majority with any strictly proper scoring rule has a regret that's at least 2 plus gamma, where gamma is a strictly positive constant, times that of the best expert in hindsight. So there is a gap between what we can do with altruistic experts and what we can do with selfish experts. Also, I think I forgot to mention this earlier. All of the results that I'm talking about now are for the deterministic case only. I'll briefly revisit randomized setting in 2 slides. So with that, we've answered all of the questions that we had for the absolute loss function. And let me quickly put them in a brief overview together. So for the deterministic setting, if we just use sort of the standard function, ignoring the incentive issues, then there's a lower bound factor of 4, meaning we do, in the worst case, we do, the loss of the algorithm is 4 times as much as that of the best expert in hindsight. We have an upper bound for a truthful algorithm that does about 3.5 times as bad as the best expert in hindsight, or 2 plus square root 2. And then there is a gap between what we can do in the altruistic setting, and that is a gap of gamma. And then these results carry over to the randomized setting as well. So in a randomized setting, there's also a lower bound. It's here a factor 2 lower, but this does mean that if we ignore incentive issues in a randomized setting, we're not going to get a no regret or a vanishing regret algorithm. Also, if we restrict ourselves to truthful algorithms, the same kind of lower bound instance shows that there's no vanishing regret possible for that setting as well. Theodoros.
The gamma is a specific value, or is
it is different for each proper scoring rule.
But it's not something that vanishes over time.
It does not vanish. Yeah. So it's a value that you can calculate if you properly normalize, meaning you get rid of any learning parameters from the scoring function. So it doesn't vanish. It's a specific value bounded away from 0. Yeah. And then we also have an upper bound result in the paper that is based on a different scoring rule for the randomized setting. So to summarize, incentives matter in machine learning. Machine learning is, in case you haven't noticed, it's everywhere around us, from self-driving cars to a lot of things that we do on the web. And so there are a lot of people that are working really, really hard on coming up with good algorithms for machine learning. But if these algorithms somehow change the data generating process, then it's not clear how useful those algorithms are. And I think that's one of the ways that our community, or one of the places where our community can really contribute something to machine learning. So I think this is a really sort of exciting direction to work on, and it's one in which we can contribute a lot. And so in the specific setting for online prediction, what we showed is that in order to incentivize truthful reporting with selfish experts, we have to rely on proper scoring rules and sort of the rich literature that already exists there. There are algorithms that have good guarantees, but unfortunately there is a gap in general between that and the best results with altruistic experts. Thank you.